Yes, so I'm going to talk to you today about a problem that we had and a piece of technology that we built and recently have open sourced to solve this problem, which is distributed monitoring. So if you go and read Joe Armstrong's PhD document that was kind of the birth of Erlang, he asks this kind of core fundamental question. How can we program systems which behave in a reasonable manner in the presence of software errors? And it's nice to think that you could just get rid of all software errors. You could just write perfect code. But that, it's not really possible. So one of the big things that you need for this is the ability to detect faults and to understand where faults are coming from in your system and respond to faults in your system. And so the answer to this question is kind of where we get Erlang, and then on top of Erlang, Elixir. So we're going to start with some basics. The first thing we're going to talk about is spawning. So here is a line of code in Elixir that spawns a process. So the spawn function spins up a new process, and then whatever code you have in the function lives in your process. There's a program counter that's running through the code in the process. So IO puts hello world out. Spawn returns the PID. Then the program counter moves forward and sees that there's no more code to run. And then our process goes away because there's nothing else to do. And so if we ask, is that process still alive, we'll see a false. So we have now learned, or you probably already know because of this audience, that processes are where code runs, and when a process is out of code to run, the process dies. So we need to know when processes die. So there are two different primitives that we have to know this. One is linking, and so when you link, you need two processes. Links are bidirectional. Luckily, if you're in IEX, you already have one process, the IEX process. We can spawn link, so that's an atomic spawn and link. Another process. Now links only fire when a process ends not normal. So a normal exit is just, I've run out of code, I've done all the things I was supposed to do, now I'm done. So here I've forced it to exit non-normally by exiting abnormal with the exit function there. So the spawn part spins up a new PID, the link part creates a bidirectional link between the two processes. And when the abnormal exit happens, the link fires, and what it does is it crashes the other process as well. We're saying these two processes depend on each other. And if you do that in IEX, you get this error message, and your IEX session will actually continue forward because they considered that you might do something silly like this in your IEX. So the other thing that you can do, though, is you can say, I don't want to crash when another process crashes. I just want to be notified. I want a unidirectional link, and those are called monitors. So again, we need two processes, so IEX is a process, and we can spawn monitor a new process. The spawn is going to spin up a new process. The monitor is going to establish a new monitor. What we're going to get back is a PID and a reference. So the PID is the process that just got spawned, and the reference is a reference to the monitor. And we can use that when we're looking at the down message. So once that process is done, the monitor is going to fire to say, hey, that process went away. And what's going to happen is we're going to get a message in our mailbox, and when we're in IEX, we can use flush to look at our messages. And so that message is going to look like this. We're going to see that it's a down. We'll get the reference that ties it back to the monitor. It's going to tell us what went down, a process, and the PID. And it's going to also tell us the reason that it went down. In this case, we just ran out of code, so the reason we went down is normal. All right. So the context of, this all works, right? This should not be a surprising part of the talk. But the context for what we were doing at Discord is that we have a real-time chat application. So kind of the hello world of Elixir, but just we've been doing it for a while, so it's very big. Here's what our product looks like if you've never used Discord. On the left-hand side, we have these things called guilds. Externally in the community calls these Discord servers, which is very difficult as an engineer at the company because we also have like physical servers and servers, and servers is an overloaded term. So we call these guilds internally, and I'm going to try my best to refer to them as guilds throughout this talk. And then over on the right-hand side, we have sessions. So these are all the users that are in a particular guild, and they have a session. They have an active session that we can send messages over. So here's some examples to make this make sense. We could have a guild for Elixir. We could have a guild for cryptography. We could have a guild for evil plans. And then we could have an even more evil guild for PHP. And then we can have some sessions. So we can have Alice and Bob and Eve and Lars. And this relationship between guilds and sessions is many to many, right? So Alice and Eve could be in the Elixir guild together. In classic fashion, Alice, Bob, and Eve are hanging out in cryptography. Eve and Lars are in evil plans, and Lars is just by himself in PHP. So the way that Discord works at its core is it's just a fan-out system. So Eve might want to send a message to the cryptography server. So she sends MD5 is the best because she wants to eavesdrop on Alice and Bob. That goes over to the cryptography server, and the cryptography server does some permission checks. It figures out who in the guild should be allowed to see this message, and then it fans it back out to everybody, and their clients get this message, and they paint the screen, and everybody can see the chat message, and we've accomplished real-time chat. But there are other messages that we care about as well. Let's say that through a programming error, Eve's session has crashed. Well, we want to have a monitor established between the guilds and sessions so that that will turn into a down message, which will get sent to all of the guilds that Eve is a part of, so that those guilds can turn those into semantic messages, like Eve has disconnected from this guild, and then fan those back out to all the people that makes sense to. And we can see here that we want monitors and not links, because if we had links, if any person in the guild crashed, it would crash all the guilds, and then if there were more links, it would then crash all of the people that are in any of the guilds that they share with Eve, which would be bad. So we want monitors, and that's why this is ZenMonitor and not ZenLink. That's it. So everything works if you only have 4 processes on one side and 4 processes on the other. But we had to scale this pretty simple idea. So in theory, these processes run in abstract, infinite, universal compute fabric. In reality, they run on machines, which are hard-edged squares. So we could start with a single computer called Discord, and we could just co-locate our guilds and our sessions, and this all works great. But as you might imagine, there's only one Elixir language, but there are lots of people who like Elixir. There's only one Erlang language, but there's lots of people who like Erlang. So these things kind of scale at different rates, and at some point you need to add more machines. And so the first thing you do is you separate it out functionally, and you go, well, these processes are kind of different-y. One is a guild, one is a session. So let's break these out into 2 boxes, a guilds box and a sessions box. And sessions keep growing and growing and growing. And so we know how to solve problems like this. You can horizontally scale, and you just add more computers, and this all works great, and distribution makes everything happy. And similarly, now there's more programming languages, there's video games, there's art communities and music communities, there's lots of people who want to talk, there's lots of groups of friends. So we start getting lots of guilds, but we have a pattern for this. We just create a horizontally scaled guild side, and then we end up in this full mesh distribution, and network cards start lighting on fire, and things go bad. And so we have to build solutions for this. So what are the problems that we faced in this full mesh distribution? The first is thunder, as in thundering herd. So in this scenario, we have a single guild, a popular guild, with 100,000 sessions attached to it. And that guild crashes. And what we see, if we look inside the guild when it crashes, if you attach observer, and this is a test, so this guild's not really doing anything, but we see that right after the crash, we get 100% scheduler utilization. One of the schedulers jumps all the way up. And if you imagine that this box isn't just sitting there having one guild, but actually doing something, your schedulers are going up and they're starving out legitimate work. On the sessions box, we see about 90% scheduler utilization as it's trying to dispatch 100,000 down messages to all of the sessions. And we also see like all of the schedulers are impacted. And so we have this like unbounded short spike of work, which is not great. The next thing that we saw was starvation. So we're going to kind of reverse the scenario this time. Let's say that we have 100,000 sessions on Discord Sessions 2 here. And that box, GCP decides you don't get that box anymore, and they shoot it in the head. And we get a node down. Well, suddenly, if we were to look inside of that guild process, we would see its message queue looks like this. There's some work to do, some real messages to process, and then there's 100,000 down messages that it has to get through. And even if those are trivially processed, that's a lot of messages to process. And if you have any receives or selective receives in your code because you expect, oh, my mailbox is only going to be about 10 or 100 things, and suddenly your mailbox is 100,000 things, like those operations are now slow. And that can cause other failures. And this is a very bad way for a process to fail because it's not fully failed. It's like it's actually doing stuff. Like it's making progress, it's doing work, it's processing through these messages. But from the outside world, it looks like I send it messages and nothing works. I send it gen calls and my gen calls are timing out. And if other processes are gen calling at it and doing the reasonable thing when they see a timeout, which is they crash too, what we saw was a cascade of failures kind of rippling out from the initial failure as other processes said, oh, I should crash too because I can't talk to this guild that I need to talk to. And the last problem we saw was one we didn't expect to see, but amplification. So if you've got a guild and it crashes, and your guild maybe is large and has a very big stack trace, it's dumped its state into its crash message. Well, that's the reason in the down message. And so that reason is going to get fanned out to all those boxes. And then it's going to get duplicated for all the sessions on those boxes. And then, like, the sessions host just burst into flames, and we take the entire service down, and we have to restart the Discord, which is something we try to avoid doing, is restarting the Discord. So now I'm going to talk about the design for the solution that tries to solve these problems. So the first design principle we had was local. We knew that transiting data over the network, one, used a lot of network stuff, but also was, we saw issues with it. So here's another quote: local monitors are fast and efficient, and that's me. So here we have a guilds box and a sessions box, and they've got like a local part of ZenMonitor and a proxy part of ZenMonitor. And we've got some processes here, a guild and a session. So with ZenMonitor, when you want to monitor a remote process, what you do is you ask the local ZenMonitor system to monitor that remote process. It creates a connector that can connect to that node. The connector establishes a node monitor to that node. So this is one of the only distribution-based monitors we have. The connector is told about this. It's going to send a message to the proxy, and then the proxy will establish a local monitor. And this all works, but the reason that PID 110 wanted to set up a monitor was to know when PID 245 goes down. But the only one who's going to know that 245 went down right now is the proxy. So let's see what happens when it goes down. The monitor fires, the proxy is informed, the proxy finds a batcher for the process that cares about this. The proxy lets the batcher know. The batcher sends a message back to the connector saying, hey, that process you cared about is dead. The connector lets the local know, and then the local lets the process know. And so there's a little bit more latency and a sort of Rube Goldberg machine in between your monitor and your message. So we've effectively complicated the situation, which is the first step towards solving the problem. So the next part that we introduced was throttling. Here we have an example that I'm sure we're getting sick of, 100,000 sessions on one box, and that whole box goes down. So our node monitor for our connector is going to fire, and our connector is going to expand that out into 100,000 messages. But luckily for us, and if you were watching the keynote that Jose just gave, we have GenStage on our side. So our local ZenMonitor process is actually a GenStage producer. And there's a new box called the dispatcher, which is a GenStage consumer. And it is going to, at a controlled rate, based off of some configuration that you can provide it when you set the system up, send out these messages. So you can control the messages per second that are actually going to go to the monitoring process. And the last thing the last design principle that we had here was to batch stuff, which we called one of the things batcher, so this should not be a surprise. So we're just going to talk briefly about what things do batching here. So the first one is the connector. The connector is the thing that effectuates monitoring. So when you want to monitor, those monitoring requests get batched up by the connector. And the connector can do a few interesting things. Because it doesn't, every monitor kind of has two sides. It has the monitoring process and the monitoree, like the person being watched. So if we see that lots and lots and lots of local processes care about the same PID, the connector can do some optimization and say, I only need to establish one monitor. It needs to do some record keeping on its side, but it can say, I only need to tell the proxy on the remote node, watch this process. I care about it. And there's a bunch of processes on my machine, which especially for like our use case of having essentially chat rooms and users attached chat rooms, you often have a lot of people on the same box that are interested in one particular server because they're all hanging out in that guild talking to each other. The batcher, as the name might suggest, also batches. So when a process goes down, the proxy creates what we call a death certificate and hands it to the batcher. And the batcher collects these up, and this is mostly just so that it doesn't overwhelm distribution when it wants to send messages back. It sends back kind of a chunk of messages. And then, of course, as we kind of already talked about, GenStage works in batches, so it's also doing batching. So what were some of the benefits that we saw with ZenMonitor? So the first was calming. So we have this scenario again, 100,000 sessions and one guild. The guild goes down, and let's see what it looks like in ZenMonitor. So if we open up Observer, it's hard to see these numbers, but the scheduler was between 0 and 5%, and then it leapt all the way up to between 5 and 10%. And this is what we expect, right? And if you think about what ZenMonitor is doing, it's dispatching a single death certificate. So like it's not trying to fan it 100,000 messages out. It's just saying, this one process died. I need to let some other remote nodes know. And then on the other side, in the sessions box, what we see is the impact is slightly delayed, right? We have these batching intervals, which means things are going to be a little bit delayed. We are trading off the immediacy of seeing a down message for these other properties that we want. The scheduler peaks at about 30,000. This is in queuing things into the local GenStage producer. And then the work is distributed nicely across time. So the dispatcher is dispatching out the down messages, but it's doing it in this controlled way that doesn't impact the other processes running on this box. The next advantage we saw was interlacing. So in the scenario that we talked about before, where you have 100,000 sessions and a node goes down, with the way that we are delivering things in batches, this is what the message queue now looks like. Meaningful work, about 1,000 downs. Meaningful work, 1,000 downs. So from the outside world, meaningful work is being interlaced with the handling of downs, which means this process continues to look alive. Gen calls continue to function correctly. You can use the process. It no longer gets into this weird zombie state where it's just processing down messages. This was another thing that we got, which we did not know. When we started the project, we didn't think about this benefit. But because we have pulled the dispatch of these down messages up into user space, we can apply additional pre-processing on the down reasons before we dispatch them. So in the situation that we lose a guild, and the guild generates a massive stack trace, we have and we ship a thing called a truncator, which has a couple of knobs you can turn, but it comes with reasonable defaults. And it will take a stack trace and it will truncate a massive stack trace into a safe to deliver stack trace, which when it gets distributed across our cluster and replicated to all of the sessions that care about this process, fit nicely into memory and don't cause the boxes to explode. And I didn't have like a cool build that was like the opposite of fire. Oh, we had thought about one which was like sunglasses, but I never added it. But all the sessions hosts can now survive this. And so things that we saw in the past that would take down all of Discord, now we easily survive. So ZenMonitor is not just like a theoretical thing that we have like designed on a whiteboard. It is a thing that is ready for use right now. So first off, it has been battle tested in our cluster. Right now, we have kind of seasonal traffic, but at peak, we have 250 million local monitors in our cluster. Those 250 million local monitors are monitoring 150 million remote processes, and they are regularly delivering millions of messages to interested parties. ZenMonitor has been running in production for over a year. So we landed it authoritatively on February 20th, 2018. That was when we turned off the ability to not be ZenMonitor anymore. So since then, everything has been ZenMonitor, and I think in the first month or two we found a bug or two, but after that we have been running it successfully with very little need to fiddle around with the code for the last 10 months. ZenMonitor is instrumented. We use another open source library that we've released called Instruments. So here are some of the metrics you can get. These metrics are both give you a good sense of how the thing is operating at runtime and just like how many monitors exist, so you can have insight into how your system is working. Just like how many monitors are established on both sides, how many processes are being monitored by the proxy, how many local processes do we think we have monitors on. But then you can also get things like how quickly are events being enqueued and how quickly are batches being dispatched, how quickly are things being delivered. So we have stuff for the local system, for the connectors, for the dispatchers, for the proxy, for the batcher. That was it. Should have dropped my voice on that last one. But yeah, so there's plenty of metrics, and these metrics are just instruments, which is another open source library. You can plug in a lot of different backends to instruments. So whether you're running your own, Grafana install, we use Datadog. So this is like you can easily emit statsd. So you can have a good sense of how the system works, and that's all configurable as well. ZenMonitor is documented, which is really nice if you want to run it in your cluster and want to see what it does. So the documentation includes a full API reference. It includes detailed module documentation that explains how every part of the system works. It includes design documents that show you how things are set up and how they talk to each other. ZenMonitor is open source. So we flipped it open source, I think, Wednesday. But now you can go to Discord app ZenMonitor. It's up on Hex. The documentation is up on Hex docs. So you can easily pull this in. So if you want to get started with ZenMonitor. If you are looking at this and going, yes, we also have some of these problems. We see processes get stuck in zombie modes because they're processing lots of down messages, or we see times where like a crash over here causes crashes over there. Maybe ZenMonitor is the right fit for you. If so, and you want to install ZenMonitor, it's pretty easy. You just add ZenMonitor 1.0.0 to your dependencies. And then you go through your code base, and anywhere you see process.monitor or process.dmonitor, you just replace it with ZenMonitor.monitor or ZenMonitor.dmonitor. So yeah, I think that's actually all the content that I have. I would be remiss if I did not bring this up. If you want to solve hard problems like this and help scale systems up to billions and billions of processes, we are hiring for the core infrastructure team, which is the team. If you have I don't know how you pronounce this, Hoover app? Yeah? All right, great. If you have that app installed, you can go to the messages. There is a job listing on the jobs topic. So you can follow the link and get more information about that. You can find me or my colleague Gary, who's also on the core infrastructure team. He's sitting up front there. Come chat to us if you're interested in solving problems like this. You can always just go to discordapp.com/jobs to see all of the positions we have available. We are based right out of San Francisco, down in Potrero Hill. So that is the end of the content. Thank you all very much, and I'm happy to take any questions you'd have. Yeah, I can just repeat the question. That's fine.
Any questions? So, what do you do when the connector crashes, right? Like, do you have any sort of safeguards there? Like, how does that supervision tree work?
Yes. So the question is, what do you do when the connector crashes, or what's the kind of fault tolerance of ZenMonitor itself? So ZenMonitor does have a supervision system. Some of the stuff that I elided over in the talk is like, how does it work, right? Like you've got one monitor on one side, but maybe you've got 100 local processes that care about it on the local side. So it mostly works. There's a bunch of bookkeeping being done in ETS to keep track of like who cares about these messages, who cares if PID 224 dies, and those ETS tables are owned by dedicated processes whose only job it is to own the ETS table. There is a supervision hierarchy on both sides, so the proxy and the local system are supervised independently. And as far as we've seen, there's not a lot of crashes, but when they crash, these processes are essentially, they don't hold any important state. They can be restarted, and they will just continue working. You may lose some stuff in flight, but there are retry mechanisms that will take care of that.
Is there an upper bound in terms of the number of processes that you monitor, or is it just bounded by the virtual system?
Yeah, so the question is there an upper bound to the number of processes that you can monitor? So conceptually, yes, right? Because every one of these monitors you establish does consume some resource. But instead of consuming a monitor, it's mostly consuming ETS records. So you're essentially memory bound. But at some point, right, like this, what the system does is it turns these kind of like immediate IRTS dispatches into batch dispatches. So there is some point, depending on how quickly things are going down, where you would go, how much latency can we handle? Because if you are monitoring more and more and more stuff, you're going to increase the latency between when a process goes down and when you get the message. In practice, though, we haven't seen any significant capping. So there is some limit based off of resources. We have yet to find it.
Are you running the latest OTP with the newer signaling changes, or are you still using an older version in production?
So we are running on these boxes, I believe Elixir 1.6 and OTP 21. I believe is what we have deployed to these. So I don't know if we've picked up the latest signaling changes, which I think landed in 21.2. I'm not. I would have to check on that. So yeah. So this. But when we started this project, we were running on OTP 20, and I think OTP 19 as well. Mixed cluster.
Is there something in the open source part that only will run on Elixir 1.6, or should it be compatible?
I believe it's compatible down to Elixir 1.5, but the mixexs file would have the details. I think it's 1.5 though. 1.5 and newer.
Other questions? All right.
Great.
Thank you.
Thank you.